Hi, my name is Riley, and this is my Physics 2 Lab 5 Magnetic Braking with Faraday. So the purpose of this lab was to collect data from dropping a magnet through a conductive tube of aluminum foil in order to demonstrate induced current in Faraday's law and then compare it to a computational model. The model we used was that we dropped a magnet through a vertical tube of aluminum foil while the phone is recording in order to find when the magnet enters and exits the tube. We did this 5 times in order to calculate average time it takes to fall. The physics concepts used were the Biot-Savart law, the Faraday's law, Lenz's law, Newton's second and third laws, and magnetic flux. Our results were that the time it took in the real world experiment was 1.09 seconds, and the time it took in the computational model was 0.914 seconds, so about a second off. The system is the magnet and the aluminum tube, the surroundings is everything else, and we assume that air resistance is negligible. Magnetic and gravitational forces are the only ones acting on the system. The bar magnet acts as a magnetic dipole. Physics concepts covered. We have, again, the Biot-Savart law up in the left-hand corner, the magnetic flux density, Faraday's law, Lenz's law, and Newton's second and third laws, as illustrated here. So the experiment-related data. First, we started by marking the north pole of the magnet using the magnetometer. We placed a tube of aluminum foil vertically and recorded it dropping the magnet through the tube with the phone. And we find the time when the magnet enters and exits the tube and take the average 5 times to find the average time it takes for the magnet to fall. The length of the aluminum foil was 0.3 meters, the width was 0.11 meters, the inner radius of the tube was 0.02 meters, the outer radius of the tube was 0.23 meters, the mass of the magnet was 0.023 kilograms, and the magnetic dipole moment that we took from Lab 3 was 1.9822. And we have my trial and times on the right-hand side here. Some checkpoint questions. We can't use a ferrous tube because it would get magnetized by the falling magnet, which would alter the conditions of the experiment. And when the magnet is dropped through the tube, it falls slower than it would in free space due to the induced current in the tube, which creates magnetic fields that oppose the magnet's motion, which we see through Lenz's law. So here's my code. We started out by just entering the constants that we took from the measurements, and then we go down to create the bar magnet, which we find the magnetic dipole moment and the mu hat, and then we come over here and we define what our magnetic field is going to be, and then we create a function for our magnetic flux, which we see here. And once we find that, then the code is programmed to already give us a simulation loop, and then we go on. And once we calculate the flux, we're able to calculate the ring of the current, which is the current of the ring, which is, of course, the negative change in flux over the resistivity of the ring. And since we are assuming that the only forces acting on this are the gravitational force and the magnetic force, we assume that this is F net. And by using all of that, we can find the velocity of the bar and the position of the bar, which actually gets plugged in to the original equation to make sure that the magnet is still moving through that current, the aluminum foil here. And then, of course, we get our exit time and our enter time. We plug that in. These are the results that we see. Note that on the right, all you can see here is the blue. As the simulation was panning out, there was red that followed it all the way down. So it's looking like the red either got overruled by the blue, or the magnetic field down here or the current down here is just a little bit too outside of this loop to see. So again, we were about 1 second off. The intensity of the color on the tube indicates the magnitude of the color flowing through each ring. So I found that red is counterclockwise and blue is clockwise. Again, you can't really see the red, but it was there as it was going through the simulation. What would happen to the dynamics of the system if you flip the magnet around? Nothing would really change. The currents would be flipped, but it would still slow the magnet down. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? We start out with our forces not being balanced, but they eventually level out. And then the point of this lab was to demonstrate the difference in computational real-world models when using Faraday's law. The answer to the first what-if question, since resistivity is inversely proportional to current, the current would become very high, which would make the magnet fall very slowly. The answer to the second what-if problem, the flow of current would be interrupted, which would mean the magnetic force opposing gravity would decrease in magnitude and the magnet would fall faster. And errors that may have occurred during this experiment are a faulty magnetometer, the effect of Earth's magnetic field, destabilization of the magnetometer, nearby devices, measurement error of times, varying magnetic dipole from the previous experiment, and that was Lab 3. And that is all. Thank you.